YouTube. Today I'm going to talk about the digital twin modeling and the intelligent network control. First, I would like to give the laser pointer. Oh, it's very small. Okay. So we all hope there is a network brain that can help us to build the optimal strategy of the networks. We can achieve higher efficiency, more capacity, lower operational costs, and so forth. But there are some challenges to this. First, the physical layer of optical networks is very complicated, which makes it very difficult to utilize the statistics of networks. Second, for large-scale networks with requirements of reliability, network control, and management is very challenging. And because of this, we have some talks today here. First one is the digital twin modeling. Second one is the intelligent network control. And this is our vision here. So we hope that we can build a DT system based on the data collected from the real system. Then we can build the AI-assisted network control based on the DT system. This is the outline of my presentation today. So there are two parts, but I'll give a very brief introduction of the first part. Then I will spend more time in the second part. So for the DT system, what we should do first is we should model the system impairments for the optical communication system. So for optical communication system, there are a lot of impairments, including the ASC noise from optical amplifiers, the nonlinear noise from propagation, the optical filtering from the wideband selective switches and transceiver, and also the implantation noise from transceiver. So there have been already a lot of works on studying each impairment here. And telemetry should be used to collect the real-time data to refine the digital models. The telemetry can be implemented in both the optical domain and the vector domain. For example, in optical domain, we have OTDR, OCM, and OPM. In the digital domain, we can use the telemetry based on the signal processing that they put in the receiver. Since there exists strong correlations among data from different sources, then data fusion algorithm is very important to extract more accurate information from the optical network. Then with the data from telemetry, the models should be refined through the process of this self-learning in order to increase the accuracy. There are two targets for the self-learning. The first target is to increase the accuracy of the model itself. The second target is to correct the parameters as the input of the model. We can use the transfer learning or the online refinement to achieve these two targets. So after we build the digital twin system, which can give us very accurate information of the real system, based on it, we can build the network control, including link provisioning, routing, and the wideband assignment, power optimization, and so forth, based on it. So in the second part of my presentation today, I'll spend more time introduce three cases for the intelligent network control. The first one is optical power optimization. We know that for optical transmission system, there's an optimal latch power to balance the ASC noise from amplifier with nonlinear interference. For example, based on this simplification here, we can see that if the latch power is too large, then we'll have a lot of nonlinear noise here. If it is too small, we have a very small SNR. So there should be an optimal lunch power for the transmission. For the wavelength deviation multiplexing systems, the nonlinear interference for all channels are different. This is a very simple case with the full loaded with wavelengths here and with identical optical power. And you can see that the nonlinear noise is different for the different channels here. So for this particular case, the optimization of the lunch power is proved to be a convex problem. After optimization, we'll have different optimal lunch powers. We'll have higher lunch power for the edge channels than the center channels here. And in real systems, this problem will be much more complex because we might have very different channel loading conditions here, and we might have different optical powers for each channel. The optimization will be much more complex than this. In addition to the lunch power at the beginning of the link, we also need to optimize the configurations of the optical amplifiers inside the link. For example, for the EDFA, we need to configure the gain and the tilt, the weight, and to determine the lunch power of each fiber span in the system. And this optimization can be conducted with the DT, but there is some problem. Ideally, we want to collect sufficient data to construct the accurate DT, and then we perform the optimization based on this DT. And then we configure the system with the optimization output. But in real system, the DT model may be inaccurate when the data is insufficient, especially during the early stages. On the other hand, the network optimization will reconfigure system and generate some useful data for the DT model to conduct self-learning. By useful data, I mean the data with very different system configurations. If we have a lot of data from the identical system configuration, the data is not so useful for the system. So in this scenario, we propose a simultaneous modeling and optimization framework for the intelligent control of the system. So the idea is very straightforward. At the beginning, we have DT, which might not be very accurate, but we still perform the network optimization based on it. And the optimization will give us some useful data, and use data, we can train the DT, and then we will repeat this process. This framework is first invested in the optimization of Raman amplification for multi-band transmission. So there are two key problems here. First is the modeling of the Raman amplifier. The second one is the gain profile optimization here. For the Raman amplifier, there is a pure theoretical model, which involves a set of the ordinary differential equations. There is no closed form solution here, and it is time-consuming. It requires additional alignment with a real Raman amplifier. Alternatively, we can use a neural network to model the Raman amplifier, but it requires a lot of data. In terms of the gain profile optimization, there will be a large number of combinations of the pump frequency and power. So it's a natural problem. So based on our simultaneous modeling and optimization framework, what we do is at the beginning, we build an initial DT of the Raman amplifier. This can be inaccurate. Then we conduct the optimization based on this TD DT. During this process, we'll freeze the weights of the hidden layers of the neural network here. We'll only change the input layer and the output layer to perform the optimization. Then we will configure the system based on the output of this optimization to the real system. This will generate some data. And we use this data to update the DT model. And during this update, we'll unfreeze the weights of the hidden layers here. We might freeze the input and the output. And this will improve the accuracy of the DT. Then we'll do the optimization again, and we'll repeat this process until we get a satisfactory performance of the optimization. And this approach is very data efficient because for given optimization target, the DT only needs to accurately model the region around that target, thus reducing the required data sets. And we will show that in this experimental results. The optimization target in this example is to achieve a flat gain spectrum, and we have different gain targets here from 1 dB to 7 dB. And we compare the framework with the baseline method. In the baseline method, we use a wild chain model with 300 data. So we need a lot of data at the beginning to train a very accurate DT model. Then we perform the optimization once. The proposed framework can achieve very similar performance as the baseline method, but this framework only requires less than 15 data to do this. And in this figure, we can see that the accuracy of the DT model gradually increases as we do optimization more times. So the idea is then extended to a neural optical transformation system in our study. So again, we have a similar problem here. If we build an offline digital twin for the entire transmission link, we need a lot of data, but sometimes we will not have that. Then from the beginning of life to end of life, the wavelengths will be added continuously to the system. In our case, at the beginning, we have 5 wavelengths, then we'll add another group of 5 wavelengths, and for each loading status, the amplifier configurations should be optimized. And the data collected during the amplifier configuration can be used for the DT construction. Here I will introduce the experimental setup. We have a 6-band fiber link with about 480 kilometers length. We have 7 amplifiers in the system. For each amplifier, we configure the gain and tune. So in total, we have 14 parameters to optimize here. And we have 6 400 gig transponders and 1 wave shaper to generate the dummy signal. And we have a SVM controlling this system, and the modeling and optimization are built inside this SVM controller. And in the result, we can see that we have 6 cases here. In the first case, we only have 5 channels. In the second case, we add another 5 channels. So we have 10 channels here, 15 channels, 20 channels, 25, 30. And in each case, we can see that the optimization will converge in about 15 iterations. And for each loading status, the amplifiers are optimized without interrupting the inverse in-service signal. This is the threshold, so they are all above the threshold. And in this result, you can see during the optimization, the accuracy of the DT gradually increases for different wavelength cases. And then for the the optimization of the amplifier, we also find that there is another important issue. After we finish the optimization of the amplifier, we need to configure the system. But in real system, the amplifiers will be configured one by one. So there is a configuration order here. And we find that different orders will lead very different fluctuations of the performance during the configuration. In some worst cases, there will be a 1 dB fluctuation of performance that will cause some problem. And so we should optimize the configuration order in this case, and it is a pretty hard problem. based on DT, we propose a heuristic search scheme for this. I will not go through the details of it, just to see the performance of it. There are two cases. In case one, at the beginning we have 5 channels, then we add more channels to 30 channels here. Case two, we start from 10 channels. And we have a lot of curves here, which represent the optimal configuration order here. So we find a worst case, as the red curve show here. There is 0.75 dB degradation of performance, and there is a 1 dB degradation of performance here. And after we find the optimal configuration order, and we can achieve the blue curve here, which you can see that there is a very small fluctuation of the performance. Okay. Next, I will go to the second control case. This one is for the failure localization. Then I will use the LODEM as an example. LODEM is a cornerstone for the dynamic optical routing in optical networks, but there can be short failures of the LODEMs. For example, there can be a filter shift and a filter patterning. And conventionally, we can use additional hardware to see if there is a failure in the system, but this will introduce some cost. And in the past few years, some schemes based on the digital signal processing and machine learning algorithm to identify the failure of the system. But in this case, we need some data, the failure data, which is very rare in the system. So can we build a cost-effective method without failure data system? What we can do is we can build a digital twin system of the real system. Then in this digital twin system, we model the optical filters inside the link. And what we can do is we can learn the parameters of the digital twin model here. Then the parameters of each function will tell us if the LODEM has a problem or not. In our experiments, we show that in a link with 10 strands and 6 weakness selective strings, we can localize the failure with 100% accuracy. We generate the failure basis with some filter shift and the filter patterning here. And in this result, you can see that if failure occurs in the first switches, in the first switch, there are 40 cases, we can identify it with 100%, and it is the same for other cases. And because we try to learn the parameters of each block in the system, then we can also estimate what's the size of the failure here, and this is very accurate. Okay. Then I will go to the third use case here. So in the third case, we want to optimize all the parameters in the transmission link, including the visual signal processing and the optical signal processing. And how do we do optical signal processing? We use the capability of the programmable weakness selective switch, and we can program the attenuations of this switch to do the optical signal processing. But there will be a lot of parameters to control in this system. So now we can do it. We can build a digital twin based on a deep neural network, and this is an entirely interpretable model compared to the real system, because for the digital signal processing, it's a digital equalizer, which is equivalent to the convolution layer in the DNN, and in the optical signal processing, again, it's a convolution. So it's equivalent to the convolution layer in the DNN. So this is totally interpretable. Then by training this deep neural network, we can obtain the optimal coefficients of the real system. And we find that with the control frequent digital signal processing, now there is almost no penalty induced by the optical filtering inside the system. All right, I will conclude my presentation. First, the techniques will build digital twin of the network that is being developed. And then the intelligent network control such as the optical power transmission and the failure management becomes more feasible based on the digital twin. The joint implementation of digital twin construction and network control should be considered throughout the life cycle for the optical networks. Thank you very much.
Any questions?
Thank you. Really impressive work. Congratulations, really nice work. I was wondering if you have plans or you're working on using the same or similar techniques for switch networks, because we have, given the dynamic variations, if you have multiple endpoints in your network.
We haven't thought about that.
So for the amplify complete order, how do we decide which order is better? Do you take the worst case or the average?
We actually try to increase the improve the performance of the smallest Q factor here.
Okay, so that is consider the worst case wavelengths, right?
Yeah.
Any questions? Please, another question?
When the digital twin starts doing self-learning, how do you calculate the error for the convergence?
That's actually a very good question, because if we want to use the data for self-learning, we need to have the ground truth.
Right.
Yeah, ground truth. So that really depends on the application cases. In this case, actually in today's commercial transceiver, we can obtain the Q factor.
Okay.